Today we're going to look at matrix operations. In particular, these three matrix operations: scalar multiplication, matrix addition, and matrix multiplication. The first two work exactly how you would expect them to. Scalar multiplication, we're just multiplying a scalar by a matrix. This works exactly how you think it would work. You multiply every entry in the matrix by the scalar. That's scalar multiplication. Matrix addition is where we have a matrix plus another matrix. This also works exactly how you think it would work. You add the corresponding entries. There's an extra requirement with matrix addition. We can only add matrices that have the same size. So if matrices are not the same size, we do not get to add them. So scalar multiplication and matrix addition work pretty much exactly as you would expect them to work. Matrix multiplication is the strange one. Matrix multiplication works differently. So usually the question is going to come up, why don't we just multiply matrices by multiplying the corresponding entries the same way we do with matrix addition? And there's a very good reason for that. That style of multiplication doesn't tell us anything useful. That style of multiplication is pretty useless. So that's why we don't do it that way. Here's how we want to think of matrix multiplication. First of all, there is a size issue. So let's let let's talk about the different issues that we have with matrix multiplication and what makes it weird. So before we go on with this, we already know how to do the operation of matrix multiplication. Matrix multiplication by, when we multiply a matrix by another matrix, is just an extension of multiplying a matrix by a vector. So I think we should probably begin with that. So we're going to extend the idea of multiplying a matrix by a vector. So if A is an M by N matrix, and X is an N by 1 vector, then AX is an M by 1 vector. And this M by 1 vector is a linear combination of the columns of A using the entries in X as weights. So it's a linear combination of the columns of A using the entries in X as weights. So there's also this row column style multiplication where you're making a dot product of a row and a column. That's another way that we could think of matrix multiplication. That's a little more operational. This is a little more conceptual. We want to think of products of a matrix and a vector as a linear combination of the columns of the matrix. But this will highlight our size requirements. Notice that A is m by n, and x is n by 1. And that so those have to match for the multiplication to be defined. And then the result will be m by 1. There's the m by 1. So the n's, the number of columns of A must equal the number of rows of X. So A is m by n. X is n by 1. The two on the inside have to match for the product to be defined. And then the outside will give you the size of the product. And that makes sense that AX looks like is the same size as all the columns of A, because we're making a linear combination of the columns of A. So let's expand this to where we multiply a matrix by another matrix. Our size restriction is still in play. So let's make a note, we have a size restriction. So those two inner dimensions have to match. The number of columns of A has to equal the number of rows of X. So let's suppose that A is an m by n matrix. Let's expand X to be a matrix. Let's expand X into a matrix. So let's let A be an m by n matrix. And let's let B be an n by p matrix. So for the matrix multiplication to be defined, the number of columns of A has to equal the number of rows of B. Because we're going to make linear combinations of the columns of A using the entries in the columns of B as weights. I'm going to specify the columns of B. So B is an n by p matrix. And we're going to say where B has columns B1, B2, all the way out to BP. Then the product A times B, the first column of AB will be the linear combination of the columns of A using the entries in B1 as weights. So that'll just be A times B1. The second column of AB will be a linear combination of the columns of A using the entries in B2 as weights. And we do this all the way across. So we're still making linear combinations of the columns of A, and we're using the entries in the columns of B as weights. So this AB1 is a linear combination. of the columns of A using the entries in B1 as weights. Then the second column of AB is a linear combination of the columns of A using the entries in B2 as weights. And so on. So this is just an expansion of what we did before as far as the size restriction goes. So if I want to multiply A, which is m by n, times B, which is n by p, if the number of columns of A is equal to the number of rows of B, then the matrix multiplication is defined. And the product AB will be m rows and p columns. So just an expansion of what we did before. Possibly the pickiest and most pedantic thing that I need to mention today, we are not using the distributive property. This is not the distributive property. If you're looking at this product, what I wrote here, where A times the first column, A times the second column, all the way out to A times the last column, if you're reading that as the distributive property, you have algebra problems that we need to sort out. Now, if you're reading this as the distributive property, and therefore you have algebra problems that we need to sort out, that applies to just about everybody. Most of you are going to have this problem. Most of you are in the category of don't really understand the distributive property, and that's okay. It's mostly because we, as a math education community, did not teach you about the distributive property properly. That's why every time you see things in parentheses, you just want to distribute, because we made it this visual thing and we didn't assign the correct words that go along with it. So it's totally normal. I'm not making fun of you. I'm just making fun of you a little bit. I know you're thinking, dude, I've been all the way through calculus. I'm good at algebra. I assure you, you are not. I'm speculating, but I almost always win that bet. So this is not the distributive property. We're just applying matrix, multiplying a matrix by a vector to all the columns of B. It's like taking that A times X and doing it for every column of B. So here are some important observations about matrix multiplication. We got to know some stuff about this matrix multiplication and what makes it weird. Matrix multiplication is not like other multiplication. And this is one of the weirder things that we experience when we get through linear algebra. As we go through math, we find out these operations that we have, addition and multiplication. We think they mean very specific things because the only thing we've experienced up until this point in our lives is real numbers and multiplication of real numbers, addition of real numbers. But multiplication and addition are things that we can apply to other objects, like matrices. So matrix multiplication is not like other multiplication. So first thing to note, matrix multiplication is not commutative. This is different than our multiplication of real numbers. When we multiply real numbers, A times B is equal to B times A. But if A and B are matrices, then AB is not generally equal to BA. So that is in general. AB is not equal to BA. For example, if I say A is the matrix 1, 2, 3, 4, 5, 0, and B is the matrix, should have picked a different matrix. Oh well. Negative 1, 0, 3, and let's go with 2, negative 4, 5. I should have done evens and odds, but that's all right. So if I calculate AB, first of all, we need to check if this is even possible. So notice that A is 2 by 3, and B is 3 by 2, so AB is going to be 2 by 2. A is 2 by 3, and B is 3 by 2. So our matrix multiplication is defined because we have 3 columns of A and 3 rows in B. And our outputs will be 2 by 2. Notice that if we try to, when we multiply B times A, we're going to get a different size matrix entirely. So B times A, B is 3 by 2, and A is 2 by 3. So the result is going to be 3 by 3. AB could not possibly equal BA in this case. Because they're going to be different sizes. So let's multiply. So I need to make a linear combination of the columns of A using the entries in B as weights. So the first column of AB will be negative 1 times 1, 2, plus 0 times 3, 4, plus 3 times 5, 0. Linear combination of the columns of A using the entries in B1 as weights. The second column of AB will be the columns of a linear combination of the columns of A using the entries in B2 as weights. So 2 times 1, 2, minus 4 times 3, 4, plus 5 times 5, 0. So first thing we have to notice is that I decided I was going to do this linear combination style and forgot it's going to take up more space than one line. So I got negative 1 times 1 plus 0 times 3 plus 3 times 5, and then I've got negative 1 times 2 plus 0 times 4 plus 3 times 0. That's my first column of AB. Then I'll have 2 times 1 minus 4 times 3 so 2 times 1 minus 4 times 3 plus 5 times 5. And then the last entry will be 2 times 2 minus 4 times 4 plus 5 times 0. And we get this 2 by 2 matrix. Negative 1 and 15 is 14. Negative 2 and 0 is negative 2. And I get 2 minus 12 plus 25. I'll do the easier one first. 2 times 2 is 4, minus 16 is negative 12. And I'm going to demonstrate my really weak arithmetic skills. I can't do 3 numbers. 2 minus, I needed more zeros is what it was. 2 minus 12 plus 25, so 27 minus 12. Oh, 15, yeah. So if we multiply B times A, we know we're going to get a completely different matrix. It'll be the wrong size. So if we multiply B times A, so first of all, we notice that B times A is going to be a 3 by 3 matrix, since B is 3 by 2 and A is 2 by 3. So the number of columns of B is equal to the number of rows of A, so the matrix multiplication is defined. And let's suppose we just want to multiply them on our calculator. So I'll put in the first matrix B, negative 1, 2, and then 0, 4, 3, 5. And I'll multiply by the matrix A. 1, 3, 5, and then 2, 4, 0. So BA is going to be, we got 3, 5, negative 5. 8, 16, 0, and 13, 29, 15. More to the point that we're trying to make, this is not equal to A times B. It's not even the same size. So in general, matrix multiplication is not commutative. Even if the product is going to be the same size, if I multiply, say, a 2 by 2 matrix by another 2 by 2 matrix, even if the sizes work out to be the same in both directions, it does not mean that the two matrices the two products will be equal to each other. And I think that's addressed in the homework. So, number one strange thing about matrix multiplication is not commutative. That is a weird thing for us to have a thing that we're calling multiplication that is not commutative. So, another thing to note. One thing to note is that matrix multiplication is associative. So this one still works out. That is A, if I have A times B times C, associative has three things. This is equal to A times the product BC. So if I have a product of three matrices, I don't need to worry about the parentheses. I can just write A, B, C, just like with numbers. So that part of multiplication still applies. So associative property for multiplication with numbers, if I have 2 times 3 times 5, I can read this as 6 times 5. I can read this as 2 times 15. Since multiplication of real numbers is commutative, I could read this as 10 times 3. But I'm not going to do that one. Because that would require changing the order. And matrix multiplication is not commutative. But matrix multiplication is associative. Another nice thing that is familiar, matrix multiplication does distribute over matrix addition. So this is another familiar thing that we do get with matrix multiplication. That is A times the sum of B and C is equal to A times B plus A times C. So we get that one. Notice that for the matrix addition to be defined, B and C have to be the same size. So assuming that the product A, B times B plus C is defined, then we can use the distributive property. If AB is defined, then AC will be defined as well because B and C have to be the same size. And that means that A times the sum of B and C will also be defined because B plus C will be the same size as B and C. So here are some things that we need to know about matrix multiplication. The big one is matrix multiplication is not commutative. You can't just change the order of your product and expect it to be the same. The other weird things about matrix multiplication have to do with the fact that not all matrices are invertible. Now, this is familiar. We've seen this before. When we say not all matrices are invertible, we mean not all matrices have a multiplicative inverse. This is true for real numbers as well. Not all real numbers have a multiplicative inverse. But in the case of real numbers, there's only one real number that doesn't have a multiplicative inverse, and that's 0. With matrices, we have lots of matrices that don't have a multiplicative inverse. So we need to talk about multiplicative inverses, and that's going to require us to talk about the identity matrix. All right, let's pause the video here, and then we'll come back and we'll talk about inverses of matrices. I'll go with inverses and identities because it's then the I and I, like Dungeons and Dragons, mazes and monsters. All right, let's pause the video here and then we'll come back and talk about the identity matrix and inverse matrices.